In physics, we talked about something called periodic functions. They were graphs that had repeating patterns. And the repeating patterns would go usually up and down, but they would go up to the same height and down to the same height, up to the same height, down to the same height. So in this particular graph that I've given you here, we want to determine if this is a periodic function. Does it go up and down to the same height every time? Well, it goes down to 0, but each spike has a different height. So we would say that this is not periodic, as opposed to this particular graph where I want you to notice that it goes down to 0, but each height goes up to 4. Oops. So we would call this periodic. Now the next question is, what's its period? The period was the interval along the x-axis for which the graph begins to repeat its pattern. So we're going to start at some point on this blue graph. Well, we start here at 0 because that's the easiest place to start. So what does the graph do? So first the graph goes up, and then it comes back down, and then when it comes back down at x equals 3, it goes back up again and down again. So that shape repeats itself. So one period of this graph we would say is 3, because it went from 0 until 3, and then it repeats its pattern from 3 to 6, and then even though we didn't give you all the graph, we would assume that from 6 to 9 it would repeat its pattern, and then from 9 to 12 and so on. The most famous periodic function are your sinusoidal waves, like the sine graph, which we've already discovered in a previous activity in class. The sine function is periodic because it goes up to the same height and down to the same height and up to the same height, down to the same height. And then the pattern just continues. Now, we only graphed one period of the sine wave. We graphed from 0 until 2 pi, which is 360 degrees. So one period starts at 0, and then it goes up to 1, back to 0, but then down to -1, and then back to 0, and then the pattern repeats itself. So we said that the period of the sine graph is 2 pi, or 360 degrees. The domain of the sine graph is the set of all real numbers. In other words, any number you plug in for x, you'll always get an output. You'll never get an error message. But the range, the y values, only fluctuate between 1 and -1. So the range is between 1 and -1. What I want you to notice right now are the x-intercepts. The graph hits the x-axis at every pi. So it hits at 0 pi, 1 pi, 2 pi. I could probably make a guess that it's going to hit again at 3 pi, and then again at 4 pi, and 5 pi, and 6 pi. This graph is nice because it also shows you in the negative direction, and notice that it hits at -pi, -2 pi, so I'm sure it hits at -3 pi and -4 pi. So we say that the x-intercepts are at every pi n, where n is some integer. It just tells you how many periods you've gone. The y-intercept of this graph is 0. I want you to notice where the maximums occur. So here's a maximum, here's a maximum. The maximums seem to happen at some sort of pi over 2. So what we say is that the maximum, the first place it hits, is pi over 2, and then it doesn't hit again until 1 period away. We call that 2 pi n. This is the same as saying 90 degrees plus 360 degrees n. The minimums also occur at some pi over 2's. But the first place it hits, if we go from left to right, is at 3 pi over 2. And then it's not going to hit again for another period. This is the same as saying 270 degrees plus 360 n. So in example 2, we want to find the sine of 3 pi by referring to the graph of the sine function. And we actually just did this a second ago. So let me go back to this graph. We said that the x-intercepts were occurring at every pi. So at 3 pi, the graph must hit the x-axis. Well, if 3 pi is the input, the output is going to be 0. The other thing is you can put this in your calculator. However, remember that 3 pi is radian measure. So if you want to check this in your calculator, you need to change your calculator to radian mode. Example 3, find the value of theta for which the sine of theta equals -1 is true. This one wants to know when are the outputs or the y values at -1. So let me go back to the graph. Well, here was a place where it was at -1. It was -1 at 3 pi over 2. And we said that it was going to hit its minimum of -1 every period after that. Since the period is 2 pi, we say the answer is 3 pi over 2 plus 2 pi n. So it starts at 3 pi over 2, and then it occurs every period after that. In example 4, we want to graph, not gray, graph y equals sine of x from 2 pi to 4 pi. So here was the thing. We graphed it from 0 to 2 pi. So it was pi over 2 pi, 3 pi over 2, 2 pi. So we had graphed this part. So if I wanted to continue the graph from 2 pi to 4 pi, that means 4 pi is over here somewhere. 2 pi to 4 pi is another 2 pi, which means that must be one period. What I need to figure out are what are the tick marks in between. Well, I know that in the middle is going to be 3 pi. So if this is 3 pi over 2 and this is 1 pi over 2, these seem to be going up by odd numbers. So this must be 5 pi over 2, and I bet this is 7 pi over 2. So the graph from 2 pi to 4 pi would be this. Hey, look, it looks exactly like the graph from 0 to 2 pi. Example 5, the average monthly temperatures for a city demonstrate a repetitious behavior. The model, which gives the average monthly temperature for Baltimore, Maryland, is y equals 54.4 plus 22.5 sine of pi over 6t minus 4. In this equation, t denotes the month, with January being represented by t equals 1. Find the average temperature for Baltimore, Maryland for month 10. Month 10 would be October. What we're going to do is we're just going to plug this into our calculator, but there's something you need to know. Notice this. That looks like radian measure. Before you plug this into your calculator, make sure you are in radian mode. And then you're going to type in 54.4 plus 22.5 sine of pi over 6, another set of parentheses, 10 minus 4, and then hit enter. And you're going to find out the answer for October is about 54.4 degrees, and I would assume this is in Fahrenheit. And that kind of makes sense because in October, fall, we're starting to cool off, so that seems like a reasonable answer for the average monthly temperature. The other graph that we already graphed one period of was the cosine curve. The cosine curve looked just like the sine curve if you continued it on forever, except I want you to notice what was different about one period of the cosine curve was that it began and ended its period at a maximum. It had the same period though. It repeated its pattern every 2 pi. Its minimum down here was at 1 pi, I want you to notice that over in the negatives, it's at -1 pi. I can tell you, if you follow the pattern, the next time it's going to hit its minimum, which is going to be in another 2 pi. 1 pi plus 2 pi is 3 pi. And then another 2 pi after that is 5 pi. So the minimums seem to be at every odd pi. The maximums occur at 0 pi, 2 pi, well, it must happen again at 4 pi, and then 6 pi. So the maximums are at every even pi. I want you to notice where the x-intercepts are at. The x-intercepts for the graph we did were at pi over 2 and 3 pi over 2. What's the distance between these two? It's not 2 pi. It's actually 1 pi. So the x-intercepts occur at pi over 2 and then occur every pi n after that, as opposed to 2 pi n. The y-intercept of this graph is at 1, unlike the sine curve where the x-intercept was at 0. In this last example, we want to determine if this graph represents the graph of sine x, cosine x, or neither of them. Well, first of all, remember that the sine and cosine x have a period of 2 pi. So, if you go from 0 to here's 2 pi, I want you to notice the pattern repeats itself like twice. So, here's one period, and then here's a second period. So if it's happening more frequently, then it has to be neither. Now we're going to talk about later on in one of our other sections, probably section 6.4, about how this really is a sine curve. It's just not the graph of sine of x. It's the graph of something whose period is a little bit smaller. And that was section 6.3 on graphing sine and cosine curves.